그래서 너무한 거 아니야? 서진아 너무한 거 아니야? 라디칼 리액션. Radical stabilization, radical stability up to tertiary. That was similar to carbocation. There was a hyperconjugation. Okay. Allylic was more stable than even tertiary, and that one is explained by resonance. You could use nearby pi bond. Not only one position, you can share the radical character over 3 atoms. There is resonance. That's why allylic radical was super stable. That's why allylic bromination was radical reaction. And the reagent for the allylic bromination, what was the name? The reagent? Instead of bromine?
Reagent.
Yeah, reagent name. NBS, N-bromosulfonamide. That was surrogate of bromine. Br2 is too toxic, so we use NBS. That's for allylic bromination. If it is not radical reaction, what is your product? Then HBr directly goes, Br2 directly goes to double bond, BR, 1,2 dibromo. That's an ionic reaction. Okay? Vertical reaction, allylic bromination, single bromination. Okay? That was the summary of what we have done last week. Alkyl halide, delta plus on carbon, halide side is delta minus. Carbon position is electron poor, that's a electrophile. Okay. Remove one proton. Leftover material is a carboanion, electron rich. Okay. So break the balance by removing one plasma charge means only proton is removed, 2 electrons left over. That's carboanion. That's nucleophile. Okay. Nucleophile react with the electrophile. So we learned alkyl halide as electrophile, and at least one example of a nucleophile we learned for acetylene deprotonation. If there is proton source, acidic proton, then we can add the base. That's what we have seen in the previous problem. Okay, if you can remove one proton, that leaves anion on carbon. That's one way. But alkyl halide, there is no acidic proton. In the case, I briefly tried to explain at the end of the last class. One way is This is electron poor. This is electron rich. To make this into nucleophile, you need to give electron. To make this -1, this -1, how many electrons do you need to give? 2, because this was a C plus, X minus, this is not changed. X, C plus, C 0, C minus, you need to have 2 electrons. Okay? Nucleophile, electron rich species. To make a nucleophile, break the bond asymmetrically in favor to carbon means remove 1 proton. Then carbon becomes minus. That was acetylene case. Right? Also, that is the acetylene case. It has, the molecule has the acidic proton, you can remove it by base. Base is also electron rich, can capture the proton, not acid. Okay? By base, you remove proton, you can make a nucleophile. If not, you give electron permanently by reductant. Then this side no change. This side is reduced from plus to minus. Okay? So this is the way, and this is what we are going to learn today. Okay? I kill halide, I said. Halide, 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 no halide, right? You cannot do anything with this. There is no halide. And you cannot make that acid halide. Let's check. Alcohols, OH, usually is not good leaving group. To make it good leaving group, one way was protonated. If proton is added to oxygen, that leaving group becomes, originally was OH minus was a leaving group, which is not good leaving group, but now water. Water is a better leaving group, that's one way. Activate OH side, and Cl minus attack behind, push out that water. That's actually halide formation. So that's rough condition, that's why a little more surface condition, activating alcohol. So we have to repeat this later. Anyway, this was the condition. And NaOH is base. If you add the base to alcohol, what can you get? Base is added to alcohol. Aldehyde. Alcohol to aldehyde is an oxidation reaction. Think simply. There's OH. If you add the base, what happens? 앞말이다 막 하지 말고 OH and you add a base, then what happens? Base 오르말 해도 좋아. What happens? 내가 앞에 뭐라고 했어? If there is acidic proton, base can capture it. Which is acidic proton here? In alcohol, OH is H, is proton source, right? That's why OH containing solvent we call protic solvent, because it has proton generated. Means OH is H is acidic proton. Can be removed, then what do we have? O minus. O minus is electron rich. That's in group. Okay? Any position, if there is proton source. Proton source means acidic proton position, then it can be removed by base. Base remove that and leaving anion behind. That anion becomes nucleophile. It can be carbon nucleophile or oxygen nucleophile. Okay? one can generate nucleophile, not alkyl halide. Okay, so this reaction should happen. Water should be removed first, and then react with the bromide. So last time we said this can react at the same time. Water is formed, and then water is formed here. Here, if protonation happens on oxygen, the particle charge. Now, two ways. One way is Br come from behind and attack, push. It can happen at the same time. That's one possibility. The other possibility is this dissociate first. Dissociate first. Here the dissociation, if you look at, this is not homolytic dissociation, this is also heterolytic dissociation. This electron pair was moved to this side. That's why this becomes neutral water. This becomes, what is this? Example like this. This one? Chomba. What is this? Carbocation. Okay. Carbocation is formed as intermediate, then which is more preferred? Tertiary carbocation is more preferred than secondary and primary. Okay. That's why this reaction works. Then utilizing the carbocation intermediate and go to the product. So we are going to learn two different reaction mechanisms next week. I'm just giving you warming up for that. For making these reactions, nucleophile react with the electrophile. One way is in one case, attack, push out, one reaction, or two-step reaction, dissociate first, and then this react with the bromide. Okay. Two way is possible. We are going to start a little more detail later. That's kind of a overview. Okay. Now, first topic is how can you change alkyl halide, the electrophile, into nucleophile? What is the answer for that? Somewhere? What did I say? How can you make alkyl halide into nucleophile? What do you need to use? 너 대답도 안 해놓고 뭐 어쩌게? 서진아? What do you need to add? 응? 응? Reductant you need to add. That's one condition is developed by chemist name Grignard. That reductant is magnesium powder. Magnesium becomes 1 plus or 2 plus? 2 plus. So then, how many magnesium do you need for this reaction? 얘기 다 해줬잖아. 뭐? alkyl halide, carbocation to carboanion. How many electrons do you need? 2 electrons, right? One magnesium atom can provide how many electrons? 2 electrons, right? for conversion of one alkyl halide to carbon anion, how many magnesium do you need? One magnesium. Okay. So the reaction, so this is alkyl halide. Okay. Magnesium provides that electron to carbon, 2 electrons. So, and the result looks like this is inserting inside here. And if you look at here, this is a 2 plus, minus 1, minus 1. Okay, that's what happened here. This reaction is oxidation reduction reaction. Electron from magnesium is provided to organic molecule. 2 delta plus extreme case plus 1 minus 1, that's oxidation number. Right? That was originally electrophile, electron poor. Now, by getting electron from magnesium, it becomes minus 1 by getting 2 electrons. Magnesium provides the 2 electron here and then it is inserted inside here. For the magnesium was oxidized or reduced. Oxidized because it was from 0 to plus 2, right? It's oxidized. So this kind of reaction, metal inserted in between two organic molecule and itself is oxidized. It provides electron. Okay? This is oxidative insertion. Oxidative insert means 집어넣는 거. Okay? Oxidative insertion. So this reagent, all of a sudden, originally this was a good electrophile, delta plus. If there's any nucleophile can attack here and then push this out. Now all of a sudden this becomes nucleophile. Now it cannot attack by nucleophile because it is electron rich. And this one can react with this. It can attack here and push this out. And this one just leave it out. So this is R minus. This is the dramatic change from alkyl heteroatom. Any kind of heteroatom is electronegative. So this alkyl should be positive. Now we changed it into negative. How? By reductant. Now this reductant, this reagent, to make it, you start with alkyl halide and add magnesium. Magnesium is metal. To make the magnesium surface bigger, you can make it grind and then make a small powder. And the surface area becomes bigger. Okay. And then it starts to react and insert here, it generates this reagent. This is the so-called Grignard reagent. All of a sudden, we made nucleophile. The other method was adding base, remove proton. There was one way to make nucleophile. Now here, by reductant, by providing electron, we made nucleophile. Now this nucleophile, to make this is made. Okay? Grignard reagent is made. And then if you have water here, what happens to it? This is C minus, negative charge. Electron rich meet with the water. Electron rich react with the electron poor one. Right? In water, which one is electron poor? H and hydrogen. You should call proton because it's H plus. Okay, H. You didn't specify whether it's H plus, H0, or H minus. Okay, the more specific answer should be proton, H plus. Okay, H plus react with these, then what can be the product? If H plus is added here, look at this. H is added. Wow, nice job. What is this product? Hexane. If you get the crude oil, then we get a lot of these. And by adding chlorine or bromine, we made this. Alkyl halide is very important intermediate. And then by adding water, you just send it back to the very cheap solvent. This is the so-called side reaction. This is a water-sensitive reaction. Means this Grignard reagent, if you have a small moisture, then it destroys the reagent. It just make it solvent. That means it's something you should avoid. Okay? That means Grignard reagent is water-sensitive. And then that reagent, if you mix with water, then the reaction fails. We wanted to have alkyl halide and then making connection to that. But if you are not careful, if there's any small amount of water, proton is much faster. It destroys the Grignard reagent. But sometimes it can be useful reagent like this. If the goal is we wanted to exchange that bromide, the bromide with the deuterium, isotope of hydrogen, then this reaction can be very useful. How can you do it? 동원이가 뭐라고 얘기하려고 현목목? 뭐 먼저 얘기한 사람 먼저 현목 먼저?
마그네슘 넣고
마그네슘 넣고 What do you make?
파우더.
Powder, okay, that's English. And
아,
what do you make?
D가
After you add magnesium, so then you can make a Grignard reagent, and then what do you add?
D2.
D2O, then you can make it. If it's intentional reaction, then that's possible reactions. At least the specific position deuterated, that's not easy reaction. So if you want to replace proton, hydrogen, but with a different one, either D or T, tritium, then maybe this reaction may be possible reactions. If not, you don't want to destroy the Grignard reagent. Okay. Very similar reactions you can do with the lithium. Magnesium becomes magnesium 2 plus. Lithium 1 plus. We have seen this lithium reagent in reduction, hydrogenation 1 by 1 onto alkene or alkyne. We have seen. On the alkyne, if you add this, then one hydrogen added, and then we form, and then the other one added, so it forms a trans alkene. So lithium is also the reductant, reducing agent, but provide only 1 electron. That's why you need the 2 electrons. Okay, magnesium case, it has a double the bond forming, that's why it is floating in the middle. But in this case, it's only one on the one hand. So one added here, one is reacted with the bromide. But property of this is very similar to Grignard reagent. Carbon character originally +1. Now it becomes -1. So property of the reagent is very similar to Grignard reagent. If you add water, what happens? You get alkene, very cheap alkene. Butane, hexane is a solvent. You can buy 10 liter. Okay. This reagent you can buy 100 milliliter 100만 원. 10 liter 10만 원. You don't want it. Okay. So this is the way Grignard reagent and alkyl lithium reagent. These are how to make the nucleophile by reduction using metal powder. Okay. Now, these reagents, as I said, they are too reactive. If there's a small amount of water, it catches the water first. And relative reactivity to carbon is relatively really small. So these reagents, we say, lithium, magnesium, they are satisfied octet rule, right? Lithium has 1 electron out of the outer shell, removed, and it's a closed shell. Magnesium also has a 2 electron outside, removed it, it's also closed shell. It's a shape of like a billiard ball, like a bamboo one. It's very hard. If it's a hard, then this becomes also hard. This becomes also hard. So this is isolated H plus, this is isolated the carbon minus. So this kind of the nucleophile is called hard nucleophile. Hard nucleophile prefers hard one. Proton is hard. It's very small and tight. Carbon is relatively soft than proton. It's a little bigger and more electron. So those characters we call soft target than proton. Then make this carbon a little softer to the left rather than this hard metal and a little soft metal. Which one is softer? If it's a closed shell, then that's a hard, we said. If there is a little flexible electrons in and out, like transition metals. Transition metals, they have d electrons. S electron field, p electron field, and then they start to add d electrons. D electrons are not fully closed shells. It's a little in and out. That's why transition metals sometimes couple 1, couple 2, they are flexible to give and take electrons. Those are relatively softer. And by mixing that, now here in this case, couple 1 was added, 1 plus. And lithium is also 1 plus. And it can be exchanged, those metals. And then it can form this kind of complex. Altogether, still the charge is the same. Carbon minus 1. Minus 1, minus 1, plus 1, plus 1. Just it's mixed together with the different metals to make the carbon a little softer. And exact structure of this, we don't know. Just by adding some amount of copper source, make mixture, and hoping that the carbon becomes a little softer. And that reagent was made by chemist named as Gilman. So this reagent is called as Gilman reagent. So after making alkyl lithium, it's a little too hard. So by adding metal ion, not metal powder. If you add metal powder, that's reductant. But here, metal ion, it's just the exchange of those metals, like alloy, half-coat. By adding metals, just the adjust the property. So general property is the same. Carbon minus, but a little softer. Then this reagent is working better for attacking electrophile. So this is typical electrophile we learned, alkyl halide. Okay. And this is nucleophile, a little soft nucleophile. And CH3 minus attack here and remove I minus. Then CH3 is empty here. This is your product. Hey, that's also alkane. Yeah, true. That's also alkane, but this is now carbon length was extended. So if you wanted to make a specific carbon number or make a branch to different reactions, now this is the way how you can make carbon-carbon bond reactions. Now we have nucleophile. Now we learned how to make a nucleophile by reduction. And adjust the property a little by adding heavy atom, transition metal, and then utilize this nucleophile and react with electrophile, and we make carbon-carbon bond. This reaction can happen. So this is nucleophile, 4-carbon nucleophile, Gilman reagent, and then this react with this. This is alkyl halide. It's electrophile, and then react with this couple, or even benzene ring, alkyl halide, and this reaction can happen. Next week we are going to learn the one-step reaction. That reaction, this is a different type. This cannot work in that way because there is no behind position to attack. But in this copper reagent, it can work this way. Generally, it is alkyl halide electrophile and nucleophile attack together and then make this coupling of carbon coupling. Details I will explain again later. So here's another example. This is alkyl halide, electrophile. This is copper reagent, this is nucleophile. Nucleophile attack here, and then it is added here. Okay. Now this reaction mechanism. Here I try to explain nucleophile attack behind here, and then push this out. This is usually what we call acid reaction, substitution reaction. But in this case, there's a little different mechanism. Altogether, this is nucleophile, this is electrophile. Product is this attack here, and then product is this one. But intermediate, in the center there is heavy atom, and then this is added first to the metal first, and then they make coupling like this. So this is also similar in a sense. Metal is inserted in between here. Previously we have seen oxidative insertion. This is ADP here, and then X is here, and then this one is removed by coupling together, and then this is recovered as copper. This is suggested mechanism for this metal catalyzed reactions. Here is extended version of a metal catalyzed reaction. Now here the metal is palladium. And if you look at here, alkyl halide, one side. And this should be nucleophile. In a sense, it's kind of a nucleophile because boron carbon, which one is more electronegative? Carbon is a little more electronegative. Boron is kind of metal, okay? Weak metal though. So this is kind of like the metallic carbon. This has a slight positive negative charge here, not strong enough. That's why it needs this catalyst to activate it. So typical reaction here is utilizing palladium as catalyst, and then one alkyl halide and one boron reagent. And if you couple, then if you don't think about this, then this is a nucleophile, this is electrophile, and this is connected together. Aromatic ring was connected together. This reaction is impossible for common substitution reaction. But utilizing this palladium, now it's possible. The mechanism is explained below. Now, originally the palladium was, let's say, palladium 0. It has a ligand, it's solubilized, but it's like palladium powder. Now, the first one, alkyl halide. To this alkyl halide, palladium was inserted in the middle. Then aromatic ring here, and then halide here. This is inserted in the middle. Reaction mechanism is very similar to Grignard reaction. Alkyl halide was there. Palladium was inserted in the middle, and palladium becomes +2. And that means that this aromatic becomes -1. Okay. -1, -1, and palladium is inserted in the middle. This is, what is the process of this? I told you several times. Oxidative insertion. Okay, this is the oxidative insertion. This is added and then activate this aromatic, make electrophile, in a sense, electron poor into electron rich. Okay, and then this one is originally it has a negative character. Now this is added here by removing this one X. This one doesn't have anything about oxidation reduction because this is minus, X is also minus, this is the exchange. Okay. So this was added. And then these two make bond, and then palladium is recovered as 0. This was -1, this was -1, right? And they becomes 0, 0. That means they return 2 electron to palladium. Then this was a 2+, it becomes original 1, palladium 0. then this is reduction. And this was dissociated from this. That's why this process is called as reductive elimination. This type of reaction is a very useful modern chemistry topic to make carbon-carbon linkage, especially for aromatic ring to another aromatic ring. Any other method, there's no good way to make this bond. Carbon-carbon alkyl linkage can be done by nucleophile, electrophile additions, but one side aromatic and make another aromatic ring connection here. This reaction is very unique, utilizing palladium chemistry. So there's a different versions, Heck reaction, Suzuki reaction by the chemist name, but this is very unique. So previously this was taught only in graduate school course, not in the supplemental organic chemistry, but it becomes so popular, so powerful, now it's introduced a little in second year organic chemistry. Okay. The general reaction, let's look at it again. Now one side is again, this is alkyl halide, like electrophile. The other side, a little different version, but for today, boron reagent was introduced. This is 50 reaction is called the Suzuki reaction. Suzuki is Japanese, the chemist name, Suzuki reaction. And key catalyst, palladium. It's not reagent, it's a catalyst. Means it's a recovered. Reaction mechanism, now this you will see this type of mechanism explanation in organometallic or inorganic chemistry fairly often. If you can understand this cycle, then you can catch the general flow. Let's repeat again. In the beginning, there was alkyl halide. Okay. To make Grignard reagent, we used magnesium. The reaction was a reduction by magnesium. Magnesium provided 2 electrons. And then magnesium was inserted in the middle. And then made a nucleophile. In this case, palladium was inserted. Process oxidative insertion. Palladium becomes 2 plus. Then here, X is originally -1, but now this aromatic, this side is a -1. This is reduced. Becomes like a nucleophile. Now here, another one was added to the metal. And then this is -1, this is -1. They make new bond, 0, 0. And then leave out those 2 electrons, give back to palladium. Palladium was recovered as 0. So this is catalytic reaction cycle. This is step, reductive elimination. Okay. If you understand this cycle, you can get maybe very fundamental basic mechanism of organometallic over here. Okay. Oxidative insertion and reductive elimination. Okay, let's check the status change of oxidation and reduction. Now this reaction, to do this reaction, to make this, what kind of reaction condition do you need? Light, and you use the light, that means the mechanism of this reaction is radical reaction. Okay. So by giving light, you break down this one first. You generate the Cl dot, Cl radical, and that captures 1 proton, and they make carbon radical, and the carbon radical attack Cl2 and capture 1 Cl and leaving another Cl dot. It's kind of a oxidation reaction, and you got this. Comparing from this reagent, original starting material, to this, the carbon is reduced or oxidized. Is it reduced? Originally, this one was, what is the oxidation number? -4. And this one? It becomes a minus. -2. Let's look at only these two, okay? CNH. This is a +1, this is a -1, okay? this one. This is minus 1, this is a plus 1. So that becomes minus 1 to plus 1. So 2 changes. That's why originally minus 4, it becomes minus 2. Is it reduced or oxidized? It's oxidized. Number was increased. If that is confusing, then you can think whether electron was added or electron was removed. What's the case? Electron was added. Here, this proton gave electron to carbon. Now in this case, the electron was taken by chloride. Electron was reduced or increased? Reduced. That's oxidation. Electron was removed, that's oxidation. Okay? So that means, carbon-wise, this is oxidized. Oxidation reduction should happen all the time at the same time as a pair, right? Which one is reduced? Which one was reduced? Shell was reduced. Originally shell was 0, it becomes
plus minus 1.
minus 1. Number was decreased. That's reduced. Okay. So this reaction we call oxidation reaction. Oxidation reaction because our interest is on carbon. Cl2 is a reagent. So we don't care about the Cl change. How about this? Going back. Now to go back, the condition is you need to make a Grignard reagent and add water. Bad reaction. But anyway, it returns this into methane, and it's a reverse reaction for this, and definitely this is reduction. Right? How about this? This is also, we can count this, let's count this. Between same atom, it's the same, so we don't count. This is minus 2. Right? This becomes what? This is the same.
Minus 1.
This is the minus 1.
Yes.
Minus 1, plus 1, plus 1, minus 1.
Yes.
So originally it was minus 2, it becomes minus 1. Oxidized. More electron with the drawing group was added. That's oxidation. This is oxidized, this is oxidized. Which one is reduced? Again, Br was reduced. 2 oxidized, 2 reduced.
Yes.
Okay. How about this?
One.
This is oxidized, this is reduced.
Yes.
If you look at this, H was originally H plus, Br was originally Br minus, no change here. Okay? It was not changed here. Only change is one oxidized, one reduced. As a total, no changes. Oxidation, reduction status is not changing. To do this reaction, is this an ionic reaction or radical reaction?
Ionic.
It's ionic reaction.
Yes.
Addition manner of this Br, syn addition or anti-addition?
Same.
Is it syn addition? Is it syn addition? Should it be syn addition? What is the intermediate? Bromonium, making triangular structure, and Br should attack from behind. Is it syn addition or anti-addition? Anti-addition. Okay. Syn addition was typical example was metal surface, hydrogens added together, that was a syn addition. Okay? That's anti-addition. This one, is this a syn addition or anti-addition? That's not very clear because the first step is a protonation happens first, they forms carbon cation intermediate. Okay. Then one side of the carbocation forming side it becomes planar, and Br can come either here or here. That's a mixture. Maybe syn half of them, anti half of them. So this is kind of a mixture. Okay. So based on this, now we learned very basic part, and we are going to continue to think working with the alkyl halide. It can be primary or secondary or tertiary. It may react with a nucleophile. That reaction what we are going to learn next week. Next week amount is a little much, so let's pre-study a little. If it's a nucleophile attack, okay. Nucleophile we learned so far. Grignard reagent is nucleophile. Alkyl-lithium is a nucleophile. A little modified cuprate, copper added something funny material, so-called Gilman reagent, is a nucleophile. And acetylene reacted with the sodium amide by removing proton. That was a nucleophile. OH group, alcohol, if you treat with the base, O minus, alkoxide, we call it. Okay. Ide is negative charge. Bromide, okay. Hydride, amide, those are negative charges. Alcohol, alkoxide, okay. Those are nucleophiles, which is species. They react with alkyl halide, new electrophile. If they work together, attack. And at the same time, okay, I got attack. So this way, I have other groups and then I have the other way. I have a living group here. I have this structure. I got attacked by nucleophile. Then it becomes tension state, half and half. And the leaving group is leave, then moves like this. Then I have nucleophile attached on the back. If this reaction happens at the same time, two molecules react together. Electrophile and nucleophile react at the same time. Bimolecular reaction. Two reactants reacted together. Bimolecular reaction. This reaction we call substitution, nucleophilic substitution. Small capital N but small character. Okay, 아래점자. Two molecule reacted together. SN2 reaction. This term we are going to learn. Okay. Reaction happened together. Another type of reaction is this guy, it breaks first to form this. They break first. Okay? And then later it meets together with a nucleophile added here. Then the reaction profile we have seen before, something like this. What is the key intermediate? Carbocation is the key intermediate.
Yes.
Then with the decomposing of this into this, this is rate determining step. This is a difficult step. And then second step is very fast because activation value is very small. This is very fast. So second step in the reaction, the kinetics measurement, rate constant measurement, you don't see that. You only see this rate determining step. Okay? That's why if you draw this into reaction rate, constant and only reactant concentration. This reaction, we need this one and this one together.
Yes.
Reaction profile is just only one transition state. There's no intermediate. And this is important and this is important. That's why reaction rate is constant, nucleophile, and electrophile both of them are important. That means if you increase nucleophile double amount, reaction rate becomes double. If you increase electrophile double amount, reaction rate is double. If you increase both of them are double, reaction rate becomes 4 times faster. This is second order reaction. Second order reaction. 2 reagent is involved. Here, only 1 reagent is involved. Nucleophile concentration doesn't matter. Whether you add a lot or small, it doesn't matter because reaction rate is determined by this. Whether this intermediate can be formed or not, that's only important thing which matters. That's why this reaction is called, that's SN2. What do you think this reaction is called?
SN1.
SN1. This is SN1. Okay. A little more thing. SN2 reactions. Now I have this structure. I have a living group here. Nucleophile comes behind me. If this position I have nothing, let's say CH3, proton, 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 hydrogen. So this is relatively small. That means nucleophile attack, static hindrance is low. So it can attack my body and I can go and then leave. SN2 reaction, this static hindrance is very important. It's small, that works. Primary, I have 1 IQ, still that's okay. 2 IQ, that's a little heavy. It's too crowded. Tertiary, impossible. If it's a tertiary position, then SN2 reaction does not happen because it's too crowded. Makes sense, right? Now, SN1 case, to form this carbocation, which is more stabilized? Primary, secondary, tertiary? Tertiary is more stabilized. That means even same alkyl halide, if it's methyl halide or primary halide, most likely they will go to SN2 reaction because it's relatively open. If it's a tertiary, SN2 is impossible. Then, if it has a chance, it may prefer to go to this space. SN1 is preferred. Okay. So this kind of the discussion we are going to continue with the different examples. A little more we are going to learn. SN2, SN1 related to reaction elimination E2, elimination E1. We are going to learn. Okay. So this one has similar character because both of them they carry the same intermediate, carbocation intermediate. This one also bimolecular reaction, but elimination is a product, substitution is a product. So if you can distinguish these 4, then you learn half of organic chemistry. Okay, that's what we are going to continue to study next week. SN2, SN1, E2, E1 reactions. Okay, concept we have learned, some basic one we have learned. Basically, you need to figure out which one is electrophile and which one is a nucleophile. Alkyl halide is a typical electrophile. How to change it into nucleophile, that's what we learn. Okay? By reduction. Palladium or magnesium or lithium. Okay? And then couple together with electrophiles. Okay? Now you go back and then 교과서 문제 잘 풀어서 조금 더 연습을 갖춘 다음 시간에 좀 더 심화로 들어갈 때 잘 따라올 수 있도록